Let's talk about that final, almost magical step that takes the code you write and turns it into something your computer can actually run. This is the world of target code generation.
First up, we're going to get the lay of the land. How does a compiler even work? Then we'll dive right into the final phase, code generation itself. We're going to unpack its three big jobs, see the incredible transformation from abstract to concrete, and then figure out why this one step is such a secret weapon for software performance.
All right, let's start with the core problem a compiler is trying to solve. At its heart, it's a huge translation challenge. How do we take code that makes perfect sense to us humans and make it work on a machine that really only speaks in ones and zeros?
And really, that question gets to the core of what a compiler does. It's not just one giant leap. It's a carefully planned journey, a whole process that takes your high-level ideas all the way down to the physical circuits buzzing on a processor.
Okay, so this flowchart here, it lays out the whole assembly line perfectly. See that little bit of code way up at the top left? That's our starting point. From there, it gets passed down through each of these phases, getting tweaked and transformed every step of the way.
And here they are, the big 6 phases. First, the compiler breaks your code into basic building blocks. Then it checks the grammar, makes sure it all makes sense logically, and creates a sort of generic intermediate version of your code. After that, it tries to optimize that version to make it more efficient, and then it reaches the last stop on the line, code generation. And that's exactly what we're here to talk about.
All right, so we've finally arrived. After all that analyzing, checking, and optimizing, the compiler has one last supercritical job to do. This is where all those abstract concepts finally become concrete instructions for a specific processor.
So what is it exactly? Well, it's the process that takes that optimized but still kind of generic intermediate code and translates it into the specific language of the target machine. Think of it as the final bridge connecting your software's logic to the physical hardware. And make no mistake, this is a really tough job. As the famous Dragon book on compilers puts it, the demands are severe. Why? Because the code it generates has to be correct. The generator itself has to be fast. And the final output has to be high-quality code that squeezes every last drop of performance out of the hardware.
So what does a code generator actually do? I want you to think of it like a highly skilled factory manager who's overseeing the final assembly line. This manager has to make 3 critical decisions to build the best possible product.
And that manager's job boils down to these 3 primary tasks: instruction selection, register allocation, and instruction scheduling. Getting each one of these right is absolutely critical. So let's break them down one by one.
First up, we've got instruction selection. So the intermediate code might just have a generic add command, right? But a specific CPU might have several different ways to add numbers together. The code generator's job is to pick the fastest, most efficient instruction for that specific situation, kind of like a manager picking the absolute perfect tool for the job. Next is register allocation, and wow, this one is a huge deal for speed. Your CPU has a tiny amount of incredibly fast memory right there on the chip, and these are called registers. The generator's job is to figure out what data to keep in these special spots. If you get this right, your code flies, because accessing a register is like grabbing a tool from your belt, while accessing main memory is like having to run to the supply truck across the entire factory floor. And finally, there's instruction scheduling. This is where the generator gets really clever. It realizes that the order you wrote the code in isn't necessarily the fastest way to run it. You see, modern CPUs are basically like little assembly lines. They can work on multiple instructions at once, in a process called pipelining. A smart generator rearranges the instructions to make sure that assembly line is always full and running at peak efficiency.
Okay, so we've talked about the theory. Now let's see this transformation with our own eyes. This is where you can really see the magic happen as we go from a generic blueprint to a very specific executable plan.
Okay, let's look at the before state. On this diagram, find that box labeled Code Optimizer. See the line coming out of it? That's our input. Now, this makes perfect logical sense, but it's completely generic. It has no idea what a CPU register is or what specific multiplication instructions are available on the chip.
And now, here's the after. Look what the code generator did. It took that one abstract line and turned it into 2 highly specific assembly instructions. First, it moves the data from ID3 into a spot called register 2. Then it multiplies the value in that register by 60. This isn't an abstract idea anymore. It's a concrete step-by-step plan for the processor.
So this all brings us to the big question.
why do we care so much about getting this last step right? I mean, why not just generate any old code that works? Well, the answer comes down to one word: performance. Look, any basic code generator can spit out a program that works, but a great one? It creates a program that absolutely flies. And the difference isn't trivial. We're talking about code that can run twice as fast or use half the battery. That's the difference between a game that runs at a buttery-smooth 60 frames per second versus a choppy mess, or a phone that lasts all day versus one that's dead by lunch.
And what's so fascinating is the balancing act that's going on here. On the one hand, you want the highest quality output, the fastest, most efficient code possible. But finding that perfect code takes time, which slows down the generator itself. So compiler designers are in this constant battle, trying to balance perfect output with a fast compilation time, all while making absolutely sure the program still works as intended. It's a classic engineering trade-off.
So, the next time you hit compile on a piece of software, just remember this final, invisible step. The code you wrote is really just the beginning of the story. There's a whole world of incredibly complex decisions about instructions, registers, and scheduling happening behind the scenes, shaping the very performance of the digital world all around us.